cartoon I was talking about. So this is from Henson House 2008. This same paper, I just pulled the cartoon out. It shows this sort of composite structure. So it looks a lot like Gary Barnes' figure as well, but this idea of the principal rain band being more convective on this end and more stratiform on this end. And then here's that sort of composite structure of the in, up, out with that upward motion inside where the primary rain band or primary reflectivity is. But then that's also where the jet forms, is right in here. And then you can see the dashed lines indicate those other two types of circulations, that descending rear inflow, or rear inflow is not the right case in this, descending inflow, and a downdraft on the inside edge of the rain band as well. And then the stratiform portion of the rain band here. So stratiform leads to this inflow, mid-level inflow, and then the convection is the in, up, and out. And so the two work together to produce this jet-like structure in the rain band. So one of the questions I got in the break, I mean, and also you may ask is, well, what's the difference between an eye wall and a rain band? And that was part of the question that RainX was designed to address. So this project, we were trying to sample the eye wall and the rain band, and to see, going back here, is there a difference between an eye wall, a secondary eye wall, or a rain band, right? And the answer that we came up with was, I think we're still working on that data. Actually, 10 years later, 11 years later now, but that a lot of it depends on where the rain band is relative to the center, right? So I already talked about the swirling flow and the convection being filamented or stretched. But I'm going to show some examples now. So I opted to spend, to review some of this other literature, but talk a bit about more of my own, since I'm more familiar with it anyway. But I had a paper in 2012, and also a paper that Bob House led, I'll show in the next slide, where we were fortunate enough to sample Hurricane Rita as it underwent eye wall replacement. And this was the first time that aircraft was able to obtain these type of really detailed observations of the secondary eye wall. So this figure is from, it's sort of a composite from my 2012 paper. So this is Eldora observations on September 21st, and about 19Z, around 20Z. And then this is the 22nd, basically the same time, about 23 hours. So not exactly one full day, but pretty close. And if you put that on the intensity chart here, that's basically this period right here. So here's 0Z on the 21st, 0Z on the 22nd. So that would be, basically right here. At just before peak intensity, and then this is right after peak intensity. So we flew it right before it hit 160 knots, or actually it was 155, not quite 160. Unfortunately, there was no aircraft there when it was at its exact max intensity. We had aircraft going around the clock, but we missed the exact peak. But we came pretty darn close. So this is a Category 5 storm at this point. So here's the primary eye wall here. There's where the plane flew around like this. So I was on this plane that day. On this day, I was this is NRL-P3 flying around like this. I was on the NOAA P3 at this day, so I got to go through, I got to go in the middle for the first time. So that was exciting. So we did 9 eye wall penetrations at 5,000 feet. And so I say I should count as 18 because I went through a double eye wall, but they don't count it that way. They only give me 9. But it was quite exciting. We had, so we went from this to this in just 24 hours. And I think a couple of things I want to point out on this figure. First, here's the primary eye wall. This is one of those inner rain bands that I was talking about. So you can see that this convection is actually quite sheared, very strongly filamented. This is 100, in the peak here, 155 knots, almost 80 meters per second, right, basically. This is the principal rain band out here, okay? So here's the scale. This is 0, 0 is the center. So this is about 75 kilometers from the center. This is only about 25. And so you may think that this was formed from this, but in fact it was this piece here that was actually consolidated to form that outer secondary rain band. Okay? This actually just propagated out, and very quickly you see these kind of continually forming and dissipating very fast. But this has a bit more of a structure. If you look at it on satellite, it looks like a big rain band. But on the Eldora scale, we can actually see this very fine scale structure. These individual convective elements. This is a 500 meter, actually 600 meter resolution analysis in this case. And then what's quite remarkable then is, so after it reached the peak intensity, then this was mostly on this side at this point, but it did extend down over to here and over to here, not quite a full 360, but then it consolidated and contracted and then formed this beautiful secondary eye wall. And now it looks like the primary eye wall is a little weaker than it actually is because of radar attenuation. So if you remember, X-band radar has some power loss, and so I'll show you another picture where we flew in the middle of the moat. So you can see the very low reflectivity in what we call the moat region. When we flew in there, this actually is stronger than it appears. But even with the 500 meter or 600 meter resolution, there's almost no break in the line. A little break here. Now it's stitched together right here, so there's a hole. So keep in mind that this took about 35 minutes to fly all the way around. So it's not a true snapshot, it's a time series, and then we kind of stitch it together right here to make it look like one piece. But it's quite remarkable. This was some really incredible data. And so we actually, the first paper that we published on this, Bob House wrote in 2007, is in Science magazine. So here at the top is the 3 aircraft that were flying at this same time. So this is basically the same time as this here, roughly. This is 1838 to 1915. So this is 1800 to 1820, so just right before that, right? The one pass. So the NRLP3 is the blue line here, so you can see it went around, and then they found a little hole in the secondary eye wall, and then flew around in the moat here. So that's the top-down picture here, so you can see it kind of broke through, and then they went around 7 times. Just kept going around. So actually, it was 7 on the next day. I think it was like 5 around, but it was a lot. The red line here is so this plane was flying at they were flying at 14,000 feet. The yellow plane here, that's NOAA 43. They were doing a large-scale figure 4 pattern, so trying to map out the whole circulation of the storm. And they were flying at 10,000 feet. So they did this pattern. And then the red plane is the NOAA 42. That's the one that I was on that day. And I got lucky to be on that one. The person that was supposed to, I flew on the NRLP through the whole time, but that particular day, the 42 was broken the day before, and they fixed it at the last minute, and they said, we need someone to fly. We don't have time to bring anybody new. And I was in the room, and I raised my hand and said, I'll fly. So this was flying at 5,000 feet, and we were just going over and across the eye wall back and forth in a pattern like this, so to get more detailed measurements. So the great thing about this is that we can actually get multi-Doppler. So I mentioned before, if you can get 2 is good, right? 3 is better. 4. The more Doppler looks up to a point, at some point the problem becomes too overdetermined, but typically 3 or 4 radars, or what we call triple Doppler or quad Doppler, gives you the best results. And so we were able to do some quad Doppler analysis in this case. So we did, so this white line here is this cross section through here. And you'll notice the difference between this one and this one. So this is where the plane was flying on the outside of the secondary eye wall. This is where it was flying on the inside. So you can see that here that this convection is just as strong as this one. And in fact, when you take the cross-section through, you can see that the primary eye wall, the old one, is actually much stronger. It's deeper. It goes almost to 16 kilometers. We've got a beautiful updraft here. And then one of the great things about the sensitivity of the Eldora is we're able to actually get measurements down in the very low reflectivity in the ice up here and actually see that downdraft. And you can see that this downdraft starts at upper levels and extends all the way down to very low levels. So you know, anything below, so this is 3 dBz, that's basically clear air. 0 dBz is typically considered the boundary between clear air and precipitation. So it is cloudy to some degree, but also clear air is like clouds, very small particles at that point. And then interestingly, even though the secondary eye wall looks very impressive from the top down, on the cross section it's not quite as impressive, right? It only goes up to, you know, the updraft actually extends higher, but the strong convection is only up to about maybe 6 kilometers or so. So it's much weaker out there. But it's very contiguous, and the wind speeds are still quite strong there. And if you look kind of carefully, you can actually see that this updraft actually turns back down. And so that you have two circulations that are working together to create that strong downdraft in the mold region there. So, so this was an exciting result out of rainforest that Bob House published. And, so yes.
Why didn't you get the information inside the primary eye wall?
Good question. In this case, you can see actually at this altitude, so this is 1.5 kilometers here. You can see it extends in a little bit here. We can only do analysis at one level here, and I'll show you another in the next slide. One or two more. We're actually able to resolve some of this in an axisymmetric sense when we do it. But from this particular pass, we were not able to see that much in here. And largely because this was the strongest convection, so there was a lot of attenuation going from here to there in this case. There were one or two passes where we were able to get some winds in the eye itself. And there's very interesting circulations in there. But yeah, on this particular pass, we were not able to resolve that downdraft very well. But I'll show you in another slide that we were. Yeah. Okay. So yeah, so Bob in his research group and in conjunction with Wen-Chao Lee and myself helped write this paper. And then I continued some of that analysis in my 2012 paper. And so what we did for this analysis was take all the flight level data from the different flights. And I mentioned the figure 4 pattern before. So we call that a figure 4 because it looks kind of like the number 4 if you rotate that. Okay, you turn your head. But the figure 4 pattern, basically you go through the middle, and then you do a connecting leg, and then you go through the middle again. And that allows us to come up with an estimate of the azimuthal mean structure, right, of the storm. And so this is an example of one of those passes from the U.S. Air Force at 700 millibars. So there's the flight track in a storm relative sense, so 0, 0 being the center. The dots are the raw measurements over that approximately 2-hour period that it took to do this plot. And then, so you can see that there's a lot of noise in the raw measurements. But then if we actually just take the azimuthal average of that, you get the red line here. And you can see, so we can see the very classic secondary eye wall structure. Primary eye wall, about 75 meters per second on average. You can see that the peak winds, of course, were stronger than that. And then you go down and then you see the secondary bump. So there's the secondary eye wall there. And then even a little bit more of a bump out here because of the rain band. But you'll notice it may be hard to see, but the red line is quite wiggly. So what we did was apply a 10-kilometer smoothing filter to that to try and beat down some of the noise to look at just the mesoscale structure. So if we apply that filter, then we get a smoother curve, and then that allows us to calculate vorticity, because the vorticity is dV/dr. If you put all those little wiggles in, you get a lot of very noisy structure. So I did that for all the passes. So for the Air Force and the NOAA 43 that were doing these figure 4 patterns. So this is a Hofmoeller type diagram from 1830 on the 21st to the 22nd, so 24 hours. The colors are absolute vorticity, so calculated from these. The white contours are tangential wind, and yellow is angular momentum. So the time period of each flight is here. So you'll notice we had a big gap right here where we had no aircraft, and that was, of course, when the storm was the strongest. You can never have the aircraft everywhere you want it to be all the time. So I made these dashed to indicate that those are just interpolated across. We just did a simple interpolation. But what we found was quite interesting. So this is 10 to the 4th minus 4 per second. The primary eye wall, even though it's decaying in convection, is still quite strong. It's the dominant dynamic feature. You can see that it's actually contracting somewhat and intensifying. So the peak vorticity we found was when the aircraft got back. It may have been stronger here, but it's interpolated. Likewise, the tangential wind maximum is right here, so the radius of maximum wind at about 25 kilometers. So you can see that the vorticity is strongest just inside that radius of maximum wind. It has that classic ring structure that I was talking about, right? And then you can see that it actually kind of goes towards a monopole, but it's still somewhat of a ring structure. But it starts to decay at that point. What's interesting is if you look at the secondary eye wall, we actually see out at about 75 to 100 kilometer radius, right where that, let me go back, right where this broad rain band is, right here, we see this enhancement of the vorticity. And if you just look at the wind field, you can see the maximum when winds here, it decays, and then there's sort of a flat part. It goes down and it's very flat in the winds. That's why we get this enhancement of the vorticity. But then over that next several hours, you see that vorticity start to enhance and contract as it goes in. And we actually don't see a secondary maximum in the wind until much later. So the precursor actually shows up in the reflectivity and the vorticity a bit more than the actual peak of the wind. So we really, I would call this, around this time, secondary eye wall formation time, right? If you define it as a peak in the secondary circulation. Now, you also notice the angular momentum lines. They move as well. The number 1 here, this is 10 to the 6th meters squared per second. This one doesn't change all that much, but number 2 actually goes outward, and number 3 goes inward. So vorticity is the radial gradient of the angular momentum, right? So the angular momentum surfaces are coming together. So the secondary circulation here is converging air into the secondary eye wall. In fact, away from the primary eye wall. So the secondary eye wall is, in some sense, stealing the inflow from the primary eye wall at this time. But you also notice that the number 4, 5, and 6 are all coming inward at this time, right? So we've got a very strong secondary circulation that's converging angular momentum, consistent with those ideas I talked about at the beginning, right? This idea of heating in the eye wall, and in this case, heating in the secondary eye wall is actually causing an expansion of the vortex. So the vortex is clearly growing in size. If you look at, this is meters per second, so your R15 is outside. We couldn't go any farther. That's where the edge of the aircraft domain is. But if you think about the 30 meter per second contour here, you can see that that one actually is getting bigger over time. It's 33 meter per second. So the vortex is definitely getting larger as a result of the secondary eye wall formation. Okay.
Excuse me.
Yes?
In this case, the secondary eye wall is very symmetric structure in this case. So what time is the clear symmetric structure of the secondary eye wall in this figure?
Good question. Well, we didn't, with the Air Force, they don't have they have a nose radar, but they don't have the tail Doppler radar. So we don't have tail Doppler except for at this time and this time. So I don't know specifically in here when that would form. From the satellite imagery, it's around this time. So from the microwave satellite pass, but then also those are every several hours. We don't have continuous measurements from that. So, so yes, I mean it's probably right around in here that you could really see a symmetric feature emerge on the satellite imagery. I have that in my paper. I have the four microwave images, but I don't have them in the talk. So it's very clearly more like a principal rain band to start, and then it consolidates into. It does start somewhat asymmetrically and then transition to symmetry.
Thank you.
And I think that's an open research question. Actually, is exactly how that process happens, going from the asymmetric rain band to a concentric ring. Need more observations.
And I have a question.
Sure.
Did you analyze radius wind formula diagram?
No. Well, yes, I did.
Yeah.
I didn't put it in the paper because the radial wind is almost zero at this altitude, at 700 hectopascals. Yeah, there is a slight inflow. It's a few meters per second, but it's very weak comparatively. So I'm not going to show it, but we analyzed the radial wind in the boundary layer from the drop sondes, and it's quite strong. The inflow is actually almost 35 meters per second.
But we don't have another altitude.
No.
Only 700.
Yes, that's the height that they flew at to do the penetrations. So, we have some in the radar, but even the radar does not get down far enough to see the inflow typically, or the really strong inflow because of sea clutter. So we have to get rid of the area by the sea surface. Okay, so yeah, so that. I guess going back, we're connecting the dots here. So we've got this time, this is 20Z on the 21st, and then about 19Z on the 22nd. So that kind of connects these two, kind of shows the formation of the secondary eye wall. And then I put this figure together. You may notice that this looks a lot like the one that I showed from Hurricane Hugo. And in fact, I deliberately stole that idea from Frank Marks. And I really like the way that he put that figure together, and I want to try and make more figures like this. I think it's a nice way to compare. The big difference between what I did and what Frank did is that I have dual Doppler. He only has a vertically pointing Doppler. So in this case, we've got time on this axis from the NOAA 42 aircraft. That was flying at 1.5 kilometers. So not quite as good as Hugo, but safer. So the dashed line here is the altitude at which the NOAA 42 is flying. That's the plane that I was on that day. And then this is a quad Doppler analysis combining the 42 and Eldora tail radar data. And so you can see, so this is on the north side of the storm. So it's right through, so it's the red line here, it's right along that flight track. Okay, so about the same time. And so what you can see is a couple of interesting things. Here's that strong convection here in the primary eye wall. Here's the shallower convection in the secondary eye wall, just like we saw from the other figure in the house paper. But you can see that in this case, with this particular analysis, I was able to resolve a little bit more of the inflow here, not too much. The strong downdraft here going all the way down. Nice updraft here, so a secondary circulation. So you actually see the inflow turning here. So it's actually mostly outflow here, though, above the boundary layer, until you get out to this region here. So kind of weak inflow. This is 8 meter per second updraft here. This is 6 meters per second. And if you combine that with the flight level data, though, you can see you have this very broad region of tangential wind. So black line is wind speed. So it's a fairly broad secondary eye wall. This is about 15 kilometers across, where you have this broad region of 16 meter per second winds. It decreases a little bit, but not much, and then it increases to 70 meters per second here. not nearly as steep as what we saw in the Hugo case, right? The Hugo was really impressive. But we see the pressure drop, pressure falls here down to central pressure about 910 millibars or so, 915. The theta E, it increases here, it's sort of flat, and then it's a very strong increase right across the eye wall, 380 to 385 Kelvin. Incredible theta E inside the eye wall. And then look at the vertical motion measured by the aircraft. This is the scale here is, this is 6 meters per second. So I identified a few of the updrafts, 1, 2, 3, 4, 5, 6, 7. See? Yeah, go ahead. It's right at the top of the boundary layer. Yes, exactly. So we saw almost no inflow right at 1.5. I mean, it was right on the edge. So I would call this flight really at like almost the exact top of the boundary layer, very close to the top of the boundary layer. Yeah, I would love to fly a little bit lower, so in the secondary eye wall, we actually see multiple peaks, ups and down drafts. So it's on this scale, there's a lot of structure, a lot of variability. You know, the radar resolves sort of one large mesoscale updraft, but the airplane with 100-meter resolution sees a lot of detail, a lot of structure. But it's very clearly dominated by the updraft here, sort of on the order of about, at this altitude even, you know, 3 to 6 meters per second. And then you see that in the Moat region here, we actually see a downdraft of about minus 1 meter per second. So this downdraft extends all the way from the top of from the tropopause all the way down to very low levels. And then the primary eye wall, once again, looks kind of like what we saw in the Hugo case. You see these updrafts here around 6-7 meters per second at 1.5 kilometers. And then surrounded by downdrafts. So this was quite bumpy going across here when you're actually flying it. And, but then you have actually another updraft right on the inner edge of the eye wall here as well. So I think there's a lot of interesting structure, and as I mentioned, I like the way that these combining the thermodynamics and the radar data together. So I like to make more of these type of plots. It takes a lot of effort, but it's a pretty plot. Now, so then what we did was, so this is just one cross section. So I wanted to show also the azimuthal mean structure. So these are from those two times that I showed you earlier, 1936 to 2008. So this is separated by about 23 hours. So you'll notice that we're not able to resolve that inflow down here. But these are the same colors as before: vorticity, tangential wind, and angular momentum. So you can see that tall structure of vorticity, the ring structure of vorticity, very deep ring. Wind maximum here of about 75 meters per second. And then you can actually see the updraft and the outflow here. Broad outflow extending up in here. And then here's the secondary eye wall that was starting to form. So you can see that enhancement of vorticity out here. And you can actually start to see, if you look carefully, there's a gyre right here, and there's a gyre right here, and a downdraft. So in the principal rain band, you're already seeing that secondary circulation that's starting to form. Very shallow and weak at this point. If you look at the tangential wind, it's that flat, very flat, broad tangential wind that's occurring, which helps to reduce that filamentation time we talked about. And so there's very little radial shear across that region. Sort of constant wind speed helps to maintain those, allow the convection to develop in that region. The angular momentum contours, pay attention to number 2 here and number 3. If you look later the next day, so then now we have the well-developed secondary eye wall. You can see number 2 has moved outward, and number 3 has moved in. 3 times 10 to the 6th has moved in significantly. The vorticity has decreased significantly here, along with the tangential wind, from 75 to 60 meters per second. But you still see a very nice out circulation, and then you see that great downdraft here, you know, all the way in. And then it's interesting, the vorticity structure of the secondary eye wall, it's got this sort of a dip shape to it. I'm not sure what you call that, but it's got a very clearly defined secondary circulation that's distinct from the primary eye wall. And you can actually see it is both edges of that gyre. So these two are working together to produce that downdraft, as I said before, on the azimuthal sense. And this is about 50 meters per second. So in this sense, from the vorticity perspective, the vorticity is definitely building upward from the low levels as opposed to building downwards due to vortex stretching. And if you subtract the two, then you get this difference field. And so the vector difference field, it's quite amazing. The white line here is the zero line in terms of difference in tangential wind. So you can see that everywhere left of that line, the tangential wind decreased. Everywhere right of that line, the tangential wind increased. Likewise, for the angular momentum, this is a negative 0.5. This is 0.5 here. So, and if you just look at the change in the secondary circulation, you can see that there was very clearly a great enhancement of the secondary circulation out here. And then essentially, this is the reverse, right? So you can think of this as it's not a true gyre because this is just a difference field, right? But there was a large decrease in the secondary circulation associated with the eye wall replacement. And as a result, a large expansion of the vortex. Significant convergence of angular momentum into that secondary eye wall at that time. So, and then the vorticity change is positive here and negative here, right? So I like this plot. I think it shows some really interesting things, and hopefully we can get some more observations like this in the future. But it takes some good luck and time. All right, so that's kind of secondary eye wall stuff. So now I want to shift gears a little bit, and I talked about some of this on Wednesday, but I'll revisit it. The idea about vertical shear. So this is the idea, about symmetric features, but when we can also look at the asymmetric structure from the airborne Doppler radar. Yes. Oh yeah.
Before going to the wind shear.
Sure.
The figure on the top, there is a ring shape, the vorticity profile inside the eye wall, which means the necessary condition of the barotropic instability is satisfied there.
Yes.
But is it barotropic instability actually occurring or not?
Good question. I think in this case, we did not see a true eye wall breakdown during the period that we were observing it. The eye wall became very asymmetric. Go back. It was clearly stronger on this side than the other, but I think that actually is largely due to the vertical shear, not the barotropic instability. So, in this case, we did not see evidence of that really occurring at this particular time. Maybe, I think, after this, there may have been more of a breakdown and how the primary eye wall eventually did completely decay, but we don't have any observations of that, unfortunately.
But how can we confirm if the barotropic instability is occurring or not by appearance or?
One way is through the evidence of polygonal eye walls, which we've seen in other storms, but we didn't see that so much in this particular case. But so, for example, Hurricane Isabel, we see the eye wall breaking down into triangles and pentagons, and that's very clear on the radar reflectivity in that case. So I think there's more evidence of that in some other cases. So it's not to say that there's not some vortex Rossby waves being generated here, but there was not a clear breakdown, at least during this time period, right? So I say afterwards. But in other cases, we've seen where you have a very symmetric ring structure, and then that breaks down into a polygon of some kind, and then tends to reform back into a symmetric. There's a great movie loop that Sim Aberson has of Hurricane Fabian where this happens over and over again. You see that a lot in numerical models as well. So I think some of that evidence comes from the polygonal eye wall
So in the case we didn't see the polynomial eye wall structure, can we say that probably the barotropic instability is not occurring?
That's a good question. I would say probably. That makes sense to me. I think part of the challenge with that, with the idea, is that just because you have the ring structure, it does satisfy the condition for barotropic instability, but only very thin rings are very unstable. So the instability growth criteria depends on the thickness of the ring and in the magnitude of the ring. So Wayne Schubert has some really nice papers on that. But then a lot of that work is also taking that ring and then just letting it become unstable. In the real atmosphere, you of course have the convection that's continually acting to build the ring and to maintain the ring. So Eric Hendricks has some good work where he's tried to look at that, where he's added heating to the ring to see what will maintain. So I would say it's maybe not that you can't say that barotropic instability is not occurring. It may be unstable and that ring may be breaking down, but then there's also convection that's acting to rebuild the ring at the same time. So yes.
Yeah, regarding this point, could you show me some vorticity distribution in your field? Yeah, maybe let me make sure what they are. Colors indicate. So.
Yeah, I think it's actually better to see it from here.
Okay.
This one, where you can see the very clear ring. You know, I mean, if you were to define the ring as sort of maybe that red, it's in this case maybe 10 kilometers across. You know, so I don't know. I haven't tried to calculate the instability, like the growth rates. The instability.
And I'd like to see the vertical distribution as well.
Sure.
Okay, let me check. So maybe Yamaguchi-san mentions the period after the secondary eye wall formed, right?
Whenever
Whenever
the
you want to
condition is
see
necessary.
the barotropic instability.